Hello, everyone. Welcome officially to the first lectures of Principles of Electrical Engineering 2. So, in this lecture, we're going to do a quick recap of some of the primary circuit elements, resistor, inductor, and a capacitor. Very quickly, I'm going to talk about what a resistor is, what is Ohm's law, what is the equivalent resistance if the resistors are connected in series and parallel, a quick recap of Kirchhoff's voltage and current laws, very briefly what a voltage and the current divider circuits are, and very briefly overview of Thevenin and Norton equivalent circuits. I have divided in this kind of a quick recap lecture into two parts. So this is this part, and in the next part, very quickly, we're going to talk about what an inductor is, a capacitor is, some of its equations, and the equivalent inductance and the capacitances in the series and parallel format. The objective of this quick recap is to really bring you up to speed with some of the fundamentals. Throughout the rest of this course, we're gonna solve these circuits, including resistor, capacitor, inductors. Right? We're gonna use Ohm's law all the time, Kirchhoff's current and voltage laws all the time. So I thought that maybe we can do a kind of a quick recap of all of these concepts. So once you are going to come across when we are solving the circuits relevant to this course, I don't need to go back and explain every single thing every single time. So that is why please review this lecture in detail. So we will take it from there. Okay, again, this is in two parts. This is part A and this is part B. So right now we are covering part A. So what is a resistor? Again, by now you should know what a resistor is, right? It's an electrical component that dissipates power. Once you're going to hook up a voltage source across a resistor, a current is going to start to flow, right? And this dissipation of the power is essentially gets dissipated in the form of a heat energy. Another interesting thing about a resistor is it does not store energy. And why I'm trying to make this into a point is because in contrast, a capacitor stores energy in the electric field, and we're going to realize that the inductor can also store energy, and we're going to learn about that shortly in the next part of this intro lecture. We know that the unit of the resistor is ohms, right? And when we buy resistors, you can go and buy them on Amazon or anywhere else, or DigiKey. You can buy these resistors. Of course, you have to provide the specifications. What is the value of the resistance you want? What is your tolerance value? And another important thing is that what is the maximum power they can dissipate? So you can get a milliwatt or even a watt resistors as well as available from those vendors. I still kind of included that over here, this chart on how to find a resistance. So for example, these pictures are very common resistors that you use on breadboards in your labs, right? And how to find the resistance of these resistors? You just hook up a multimeter across its terminals, and that will tell you what the resistance is. So why we still need this kind of a big chart here, right? I would still see the need and the utility of this chart is because I think we are not looking at, especially the students, right? You guys are not looking at what else it has to offer other than finding the total value of the resistance. The other two very important parameters it has to offer is this tolerance values and temperature coefficients. So you can use this chart and find the total value of the resistance and the tolerance and the temperature coefficients of these resistors. So for example, in this specific case, right, so again, all of these colored bands represent certain things. So for example, the first color band represent since this is green, this is going to come out to be 5. The other one is blue, 6. The other one is black, 0. So the first digit is 5, 6, 0. Then we're going to have a red, which is a multiplier, should be 100. So you end up getting a 56 kilo ohms resistor with a tolerance of 5 plus minus 5%. So you can potentially use again this chart to not only find the total value of the resistance, also the band, also the temperature coefficients and the tolerance values. Very important. We are going to continue using these resistors throughout electrical engineering. So please get comfortable with not only the resistors but also the inductor and the capacitor that is going to come up shortly. Okay, so let's quickly review Ohm's law. So what happened was we had a resistor. Here is a symbol of this resistor. If we will hook up a voltage source, for example, a 5-volt battery or a 3-volt battery or any other battery, 9-volt battery, if we will hook up a battery to the resistor, what is going to happen? A current is going to flow through a resistor. And we're going to have a voltage drop across a resistor, VR, right? So this is what the Ohm's law is. Ohm's law states that if you apply a voltage to a resistor, a current flows, and the amount of the current is directly proportional to the voltage applied, and the amount of the current is inversely proportional to the resistance of the resistor. So we can easily say I equals to V over R. Another interesting thing. So interestingly, higher the value of the voltage, higher the value of the current. Lower the value of the resistance, higher the value of the current, right? Okay. Another interesting thing about a resistor and its VI characteristics, right? So for example, here's a resistor, you apply a voltage here, and a current will start to flow. So you can actually plot it in the form of a VI characteristics, right? On the x-axis you have a voltage, on the y-axis you have a current. So as you continue to increase the voltage, we know that over here, as I continue to increase the voltage, the value of the current is going to increase as well. So I will get a linear curve like this or like this. Now, if you will change the, if you're going to keep the Vs the same, and let's say this is a variable source where you can, or let's say you have a power supply where you can tune in the Vs voltages from 1 volt, 2 volts, 3 volts, 4 volts. You can change the values of the voltage. And that is why you can plot, and this is how you can plot this, for example, VI characteristics. You can apply variable voltage across the resistors to find variable currents. Okay, now so for example, if you get these two curves represented by the blue and kind of a pinkish purple color here, pink color here, so the idea is that which of these curves represents a smaller resistor, or which of these curves was obtained with a resistor which has a higher value, right? And how to know that? You can easily know this thing by looking at what this curve represents, right? So on the y-axis we have a independent variable current, on the x-axis we have a dependent variable voltage, right? So I can write this equation as I equals V over R. If I look at this equation, this represents a linear equation. And if you remember some of your basic maths, in this linear equation, my m is slope, where I have a y independent variable, and x is a dependent variable, right? And y and m is the slope over here. So the slope over here in this equation is 1 over r. Actually, yeah, it is equals to 1 over r. So this means that higher the value of the resistance, smaller will be the value of the slope. And the slope of this pink line is higher as compared to the slope of the blue line. So if the slope of the pink line is higher, this means that it will have a lower resistance, right? So that is why the slope of the pink line is higher, its value is lower. The slope of the blue line is higher, that is why the value of the R2 is higher. So just kind of a normal thing. You must already know all of these things, so just providing you a quick recap, right? Again, in summary, you have a resistor, you apply a voltage, or connect a resistor to a voltage source, a current will start to flow through it, which can be represented by Ohm's law. We're going to use Ohm's law hundreds of times in the course. And this can be written as V equals to IR or I equals to V over R. You can also have a voltage transfer characteristics here. Not voltage transfer characteristics because that is slightly different. You can have a VI characteristics here, which is the plot of the voltage versus the current. In a case of a plot where your x-axis is voltage and y-axis is current, the linear curve represents, the slope of the linear curve represents the inverse of the resistance, or the slope represents the conductance, right? So yeah, please understand this basic thing. Okay, moving on. Again, a quick recap. Over here we have three resistances connected in parallel, R1, R2, and R3. you should already by now know that the equivalent resistance of this should be just a summation of all of three things together, right? R1 plus R2 plus R3. And how do we get to this equation? Is a kind of a very simple thing, right? We know that the current that is going to flow through all of these three resistors, since they are all connected in series, so the same current should flow through all the three resistances. And if the same current is going to flow through all the resistances, we can also, for example, I can also say that VR or just VR1, VR2, or VR3. Sorry, this is negative, this is positive, VR3. Right, so I can also represent this thing as R equivalent equals to V over I, or V over I1 plus V over I2 plus V over I3, where all of these currents are the same. So you practically get this thing. So this is how you can easily kind of derive this equation if you really want to get to the fundamentals on how do we know that the R equivalent is equal to the summation of all the three resistances. Because the same amount of the current flows through all the resistances, that is why you can easily derive it to be the total amount of the resistance in the circuit should be the summation of all the three resistances. Very quickly, let's look at the parallel case as well, where we have all the three resistances are connected in parallel now. Interestingly, if that is true, then we know that the voltage across all of them should be the same. If the voltage, so for example, if I assume this is V1, this is V2, this is V3, then the voltage across all three of them is the same, which should be equals to V. So V should be equals to V1, should be equals to V2, should be equals to V3, and the same if you really want to put it over here, I equals to I1 equals to I2 equals to I3 over here. In this parallel circuit, again, if you were to drive it, the total current that is I coming into the circuit, just assuming over here, right, you are going to have an I1 coming here, I2 coming here, and then I3 coming through the resistor R3. So the total amount of the current is going to be the summation of I1 plus I2 plus I3. And again, you can represent I1 by V over R1, I2 by V over R2, I3 by V over R3. And since the total voltage is the same as for V1, V2, and V3, since they are all connected in parallel, so you can kind of cancel them out, and you are left with this kind of a beautiful equation. The total equivalent resistance, the inverse of the total equivalent resistance, equals to 1 over R1 plus 1 over R2 plus 1 over R3. So the idea of this slide is to understand, to let you know that although you should know by heart that if the resistors are connected in series, the equivalent resistance is the summation of them. If they are connected in parallel, then 1 over R equivalent is 1 over R1 plus 1 over R2, and all the way. Having said that, there's a reason why we end up getting these equations, and the reason is that in the series, the resistors are connected in series, so the same amount of current flows through them, and in case of a parallel combination of the resistors, the same voltage drop appears across all the resistors. So that is why we end up getting the equations for the equivalent resistance as what we get. Okay, so in terms of the circuit analysis, I would like you to still remember this thing while appreciating how do we get this thing. Okay, here is a quick recap on Kirchhoff's voltage and current laws. I found this kind of very interesting figure over the internet that I'm using. And then I'm going to show you one very quick example of the Kirchhoff's voltage law and the current law as well. We are going to use Kirchhoff's voltage law and current law many times throughout the rest of the course. Okay, so the Kirchhoff's voltage law states that the summation of all the voltages in a closed loop should be equals to 0. In this interesting example, we just have 4 resistors connected, and there is a voltage drop across all the resistors, right? So that is why the voltage drop across all the resistors sums out to be equals to 0. Anyhow, in the next slide, I'm going to have another circuit where we will have multiple resistors and the voltage source, so things will become more clear there. In case of a Kirchhoff's current law states that at a particular node, the total currents that are coming into the node should be equal to the currents that is flowing out of the node, right? We have a current I1, I2, and I3 coming into the node, right? So you have an I1 plus I2 plus I3 coming into the node should be equals to the currents that are flowing out of the node, which are I4 plus I5. So I1 plus I2 plus I3 should be equals to I4 plus I5. And of course, if you're going to take I4 and I5 to the left-hand side, it's going to come out to be minus I4 minus I5. Sorry. So the Kirchhoff's current law states that again, total current that is entering into the node must be equals to the total current that is getting out of the node. So please remember the Kirchhoff's voltage law and the Kirchhoff's current law. Let's do, one very quick examples of both of them. So that will serve as kind of a good reminders of how to solve and use these laws in the circuits. Sorry, okay. So this is an example for the Kirchhoff's voltage law. Here is a representative circuit where you have a voltage source of Vs, which is 20 volts, connected to 3 resistors. We have an R1, R2, and R3. And VR1, VR2, and VR3 represents the voltage drops across the resistors. So let's use the Kirchhoff's voltage law and figure out the amount of the current that is flowing through the circuit, and then also the voltage drops across the resistors, right? VR1, VR2, VR3. Let's find all of that. Okay, so if I will apply the Kirchhoff's voltage law, again, which states that the summation of all the voltages in a closed loop must be equals to 0, then what do we get is Vs should be equals to VR1 plus VR2 plus VR3. Okay, so this is good. We are gonna come back to this in a second. Another thing, let's find I1. Let's find the total amount of the current that is flowing through the circuit. How you can find the total amount of the current that is flowing through the circuit? You have 3 resistors connected in series, R1 plus R2 plus R3. So we can easily find an R equivalent, which is R1 plus R2 plus R3. So 15 plus 20 plus 5 comes out to be 40 ohms. If I get R equivalent as 40 ohms, I know my Vs is 20 volts. I can easily find the value of the current that is flowing in the circuit, which is going to come out to be 20 divided by 40. 0.5 amperes. So I have a total of 0.5 amperes that is flowing through the circuit. If I have a 0.5 amperes flowing through the circuit, then I can easily figure out what the voltage drops across all of them would be, right? So VR1 would be, right, the current times IR1. So the current is 0.5 amperes times 15 ohms. The answer comes out to be 7.5 volts. VR2 is I times R2, which comes out to be again 0.5 amperes times 20 ohms, 10 volts, and VR3 is IR3, which comes out to be 0.5 amperes into 5 ohms, 2.5 volts. So you ended up finding the value of the current, you ended up finding the value of the voltage drop across all the resistors. So now let's see if this equation that we initially wrote for the Kirchhoff's voltage law satisfies this equation, right? So the equation was Vs equals VR1 plus VR2 plus VR3. So the total value of the Vs is 20 volts, should be equals to VR1, which is 7.5 volts, VR2, which is 10 volts, plus VR3, which is 2.5 volts. The summation of all of that is 20 volts. So this equation holds true. So again, this is just one of the examples how you can use the Kirchhoff's voltage law, or how these circuits satisfies the Kirchhoff's voltage law. We are going to continue use both the Kirchhoff's laws, the voltage law and the current law, throughout the course. So please pay special attention to these laws. Okay, let's do kind of a very quick example of a Kirchhoff's current law as well. This is KCL is the Kirchhoff's current law, right? Okay, here's another circuit. Essentially, what do we have to do in this circuit is we have to figure out the values of all currents, right? So I want to find out the value of I1, I2, I3, and I want to find the value of the V1 as well, node voltage. So let's call this node 1. Okay. Interestingly, if I look at the circuit as is, where the direction of the currents is already given, right? I can see that my current I1 is flowing into the node, is entering into node 1. Current I3 is entering into node I1 in node 1, and current I2 is leaving node 1, right? So if I will apply now Kirchhoff's current law to node 1, for example, I can easily write this equation, right? So the summation of all the currents going in should be equals to summation of all the currents going out. So all the currents going in are I1 plus I3 should be equals to I2, right? Okay. So hope this equation can easily be formed by, can be obtained from this KCL and looking at the circuit at node 1. Okay, and this is what I just said about the currents are going in and out of the node. All right, so let's find all the values of the currents I1, I2, and I3, and also the value of the V1. Okay, so how to figure this thing out? We are going to use this equation and further solve this. What is the value of the I1? I equals, now we are going to use Ohm's law. I equals V over R, right? So what is the value of the I1? If I have to solve I1 for this circuit where this is V1, right? I can easily see that it should be V2 minus V1. I1 is V2 minus V1 over R1. I3 over here is equals to V3 minus V1 over R3, and I2 is, since the current is directly going through the V1 and is there a ground here, which is 0 volts, right? So you get V1 minus 0 over R2. So V2 minus V1, V2 is 30, V1 you don't know, divided by R1, which is 100 ohms, plus V3, we know 20 volts, V1 we don't know, divided by R3, 150 ohms, V1 we don't know, divided by R2, which is 1 kilo ohms, 1000 ohms. Okay, great. So if you were to solve this for V1, you're going to get the value of the V1 to be 24.528 volts. This is the value of the V1. Once you find the value of the V1, you can easily replace this value back over here and also in this equations to find the values of I1 and I3. Okay. Okay, so let's find the value of, starting with the value of I2 maybe. I2 is the easy one, which is just V1 over 1000. We know the value of the V1, 24.528 or 53, simplifying, divided by 1000. I2 comes out to be 0.025 amperes. So this is the value of the current. Similarly, you can find the value of the I1. I1 equals V2 minus V1, right? V2 minus V1 over R1. V2 was 30 minus 24.528 divided by R1, which is 100. I1 comes out to be 0.055 amperes. Okay, interesting. And finally, I2 is, sorry, I3. I3 is V3 minus V1 over R3. V3 is 20 minus V1, which is again 24.5 divided by R3, 150. So I3 comes out to be minus 0.03 amperes. Okay, so this is how you can use Kirchhoff's current law to solve a circuit to find out the values of all the currents. So we are using Kirchhoff's current law, and potentially while we are coming down with these equations, we are actually using Kirchhoff's voltage law, and we are using Ohm's law all the time, right? So again, this circuit, although emphasized on Kirchhoff's current law, but also use the rest of the laws as well. These laws are too fundamental and used innumerable number of times, so please get comfortable with all of them. Another important point that I want to make over here is with this I3. So in the circuit problem, we assumed, or the author who provided us with the problem, if I will make my own circuit and just assume a particular direction of a current, and I will give you a direction of the current, right? So for example, in this circuit, this I3 was assumed to be flowing into the node 1, But when we ended up finding its value, it came out to be minus 0.03 ampere. So this essentially shows that the direction of the I3 is actually on the other side. So there is 0.03 amperes is actually flowing in this direction. Or if you were to keep this direction as this, then you're going to have minus 0.03 amperes flowing, right? So essentially it's just moving the negative sign on the other end. So I hope that this negative sign makes sense, right? It's the direction of the current flowing in the other direction because our initial assumption was wrong. And the current was actually flowing in the other direction. The positive current was flowing in the other direction. Okay, so this is how you can use the Kirchhoff's voltage law and Kirchhoff's current law to solve some of these circuits. Now, very quickly, we are going to still apply all of these laws and do a couple of other interesting things, which we're going to come across in the future as well. So we are not going to derive or solve any of these things, and I would hope that you guys will remember some of these rules in the future. So there's another rule that is called as a voltage divider rule. A voltage divider rule is that, for example, let's say in this particular circuit, you have a Vs supply voltage connected to two resistors, R1 and R2. And the idea was that what is the voltage drop that is across R2? Right? So V out, and the answer to this problem is the output voltage equals the supply voltage times the resistance across which we are determining the voltage, output voltage, divided by the total resistance. So how do we get to this equation? And for the future reference, this is such a basic equation that once you're going to use it a couple of times, you're going to remember it and you don't have to go back and drive everything. But again, I am going to put a lot of emphasis on the derivation and everything so that you will understand the fundamentals of whatever the things are coming from, why they're coming from, and where they're coming from. Right? So we are just going to do it one time, but I hope that you will remember this thing. Okay. So we want to prove that in this voltage divider circuit, essentially we end up getting this equation. Okay. Oh, sorry. Next one is a current divider circuit. Okay, so voltage divider circuit, and let's prove this thing. Okay, so let's assume that the voltage drop across R1 is VR1 and across R2 is VR2. And of course, these are the same, right? And let's apply Kirchhoff's voltage law. Another application of a Kirchhoff's voltage law. We are going to use Kirchhoff's voltage law and the current laws all the time, and the Ohms law. So just consider this to be another example, right? So let's assume that, right? So we have this current that is flowing. So according to Kirchhoff's voltage law, your supply voltage should be equals to VR1 plus VR2, right? And then according to Ohm's law, we know that VR1 should be equals to I times R1, and similarly VR2 should be equals to I times R2, right? So what I'm going to do is I'm going to replace both of these things back here, where my supply voltage is going to come out to be IR1 plus IR2, taking I common, R1 plus R2. Okay, great. So let's find the value of the current. So the value of the current is going to come out to be Vs times 1 over R1 plus R2, right? So you're essentially taking R1 plus R2 on the other side. So this is the value of the current. If this is the value of the current, let's find the value of the VR2 or output voltage, this one. Okay. So we know that output voltage equals to VR2, which is equals to I times R2. What is I? This is I. I is Vs times 1 over R1 plus R2 times R2, right? So you got VR2 or V out as the supply voltage times the resistance across which we are measuring the voltage divided by the sum of the other resistance across which we are measuring the voltage divided by the sum of the resistances, right? Similarly, we can get VR1, which is I times R1. It is going to come out to be the supply voltage times the resistance across which we are measuring the voltage, which is R1, divided by the summation of the resistances. So I hope this should serve as another good example of how you apply a Kirchhoff's voltage and Ohm's law. In addition to that, this should serve as interesting how do we get to these equations. We are not going to derive a Kirchhoff voltage divider or current divider rules again, and I expect you to remember some of these things. Okay, so let's very quickly look at the current divider rule, divider circuit in the rule as well, which is slightly more interesting. And essentially, again, now you have two resistances in parallel, R1 and R2, right? And the idea is that, and V is the supply voltage, IT is the total amount of the current that it is providing, and this IT gets divided at this node into IR1 and IR2, right? So IR1 and IR2. At this node, we can call this node as A. And this is the current divider rule equations. The current divider rule is if you have to find a current flowing into a certain branch, for example, the current that is flowing into R1 should be equals to the total current, IT, times the other resistance, which is R2, divided by the total sum of resistances. Similarly, I can already write the other one as well, and then we can, of course, we're going to validate it. IR2 should be equals to I2, IT, total current, times the other resistance, R1 over R1 plus R2. Okay, so let's derive these equations very quickly. Okay, so this is another example where we are going to use Kirchhoff's laws and Ohm's law. Okay, so if this is interesting, we are going to look at node A, and I am more interested in Kirchhoff's current law over here, Kirchhoff's current law. And Kirchhoff's current law states that my total current over here equals to IR1 plus IR2, right? IT is the total current flowing into the node A, and IR1 and IR2 are the currents flowing out of the node A, right? And I have applied these currents, Kirchhoff's current law over here. Okay. So then what is the value of the IR1? IR1 by Ohm's law should be equals to, let's assume the voltage drops over here. Again, both the resistances R1 and R2 are connected in parallel, and the voltage drop across both of them should be equals to the supply voltage V. Okay, so IR1 should be equals to V over R1, and IR2 should be equals to V over R2. Okay, so let's put both of these back into this equation. The total current should be equals to V over R1 plus V over R2. You can take V common, 1 over R1 plus 1 over R2. You can do R1, R2, R1 plus R2. Okay, so let's find since the voltage across both of them is the same, so we're gonna re-represent this in the form of a voltage. So V equals to IT. Essentially, you can take this on the other side. You're gonna get R1, R2 over R1 plus R2. This is the value of the voltage that is appearing across these resistances. Okay, now let's find both of these equations. IR1. IR1 again is equals to V over R1. So you get V over R1. You already know the value of the V, which is I1 times R1, R2 over R1 plus R2 divided by 1 over R1, which should be cancelled. So your IR1 should be equals to I1. Sorry, this is not I1, this is IT. Yeah, okay. So from this equation, right, IT equals V over this. So this should be IT. So V over R1 equals IT times R1, R2 over R1 plus R2 times 1 over R1, right? So 1 over IR1 should be equals to IT, the total amount of the current, times the resistance, the other one, R2 over here, divided by R1 plus R2. Similarly, we can solve it for IR2 as well. IR2 should be V over R2. The value of the V is coming from here, which is total current IT, R1, R2 over R1 plus R2 divided by 1 over R2. So we are left with IR2 equals IT times the other resistance, R1 plus R1 plus R2. Okay. So this is how you can kind of validate both of these equations. With a very simple circuit, this is called as a current divider circuit and a rule. And once we're going to make more complicated circuits as we go down, we are going to use the current divider rules, the voltage divider rules, the Kirchhoff's laws, the Ohms laws. All of these things should be on your fingertips, right? How to use them in circuits, and these are just some of the examples. In a current divider rule, we saw another application of a KCL, and in a voltage divider rule, we saw another application of a KVL. Okay, great. So some kind of a quick comments on these Thevenin and Norton circuits. We are not going to solve all of them. Maybe go back and review your previous Thevenin and Norton equivalent circuits and the theorems lecture from PEE1. But still giving you a recap, I do want to emphasize on the concept of it. Right, so the whole idea of doing this Thevenin and the Norton theorem and the equivalent circuit is, let's just assume that you had a very complicated circuit with many different resistances, like 5 or 10 different resistances and many different voltage sources or current sources. You have a lot of these excitation sources, voltage or current sources, and then you are going to have a network of resistors. A kind of a complicated circuit. But as a user, what you are interested in is what is happening at the end of it. What is going to happen once you are going to connect at its output a certain load, right? So you are interested in what is going to happen to that load, right? How much current is going to flow through the load? What is the voltage that is going to appear across that load? And how much the power consumption is going to be there. So you are interested only at the terminal of that circuit or at the output of that circuit, right? In those cases, and we are not interested, for example, if there are 5 different resistances in that kind of a complicated circuit, then what is happening in resistor 3 or 2 or 1, or at a particular node, what is the value of the currents going in and out? We are just interested in the final terminals. So these people, Thevenin and the Norton, they came up with these kind of very good theorems and the circuits that could potentially be used to simplify those circuits. Okay, very quickly, let's look at the Thevenin equivalent. And the whole idea again was that you have this complicated circuit with many different sources, including many different resistors. And then the whole idea was we can simplify all of that into a single voltage source connected in series with the equivalent resistance, and we can look at the terminals so that once we are going to connect a particular load, we can analyze it. What's the amount of the current flowing through it, power consumption, and the voltage appearing across it. Similarly, on the other end of the things, we have a Norton equivalent circuit provides you that you still have the kind of a similar circuit, but you want to have a different representation, where what you do is, again, you find the equivalent resistance of those circuits, where R Thevenin is here, Rn is here. The process of finding R and R Thevenin is exactly the same. For a particular circuit, both of the values is going to be the same. And then what you do is, rather than finding a Thevenin voltage, you end up finding a Norton current. So very quickly, again, go back and review those lectures. In case of a Thevenin voltage comes in series with the Thevenin resistance. In a Thevenin equivalent circuit, in a Norton equivalent circuit, your Norton current comes in parallel with the Norton resistance. In that equivalent circuit. And very quickly, right, how do you find, for example, Thevenin resistance and a Norton resistance for a particular circuit should be exactly the same for a same circuit, right? Because the resistances are going to be the same, and both R Thevenin and Rn represents the equivalent resistance for circuit. So how do you find it? For considering if you just have independent sources in your circuit, you practically short circuit the voltage sources and open circuit the current sources, all of them in the circuit, and then what you will be left with in that big circuit would be just the resistors, right? So you can, those resistors will either be connected in series or the parallel. So you can solve that series and parallel circuit combination to find the equivalent resistance. And that would be your Rn and R Thevenin in Norton equivalent circuit and Thevenin equivalent circuit, right? In order to find the in order to find the V Thevenin, essentially you remove the load, or you don't consider the load and only consider the A and the B as output terminals, and find the open circuit voltage, which should be equals to the Thevenin voltage, right? And similarly for IN, essentially what you do is, again, you don't put a load there, just short circuit A and B and find the value of the current that is flowing through the short circuit, right? So I short circuit or V open circuit. So in case of, again, a Norton equivalent, you're going to short the terminals A and B and find the total amount of the current that is flowing through it to find IN. You're not shorting in this. This is the final equivalent circuit, right? So whatever the circuit over here is, essentially you're going to short these terminals to find ISC, and you're going to open these two things to find VOC over here. So this is how you find IN and V Thevenin. But again, for a more detail with examples and everything, review the other lecture. Maybe I will be able to provide some supplementary lecture with some more examples for the Thevenin and the Norton as well. But I want to do more focus on the inductor and the capacitors in the next part of this lecture, because in this course we're going to focus a lot more on the inductor and the capacitor, and they're slightly more complicated than resistors anyways, right? So we are, I want to give a quick recap of inductor and capacitor as well in the next part of this lecture. All right, so with that, thank you so much. I will talk to you in the next one. Thanks, bye.